In this video, I'm going to show how to solve a couple of different ramp problems which are very common in high school physics, and I'm going to go kind of quickly using information we've already learned in class, so I'm just going to breeze through these very quickly. Here's the first problem. A 25 kilogram block is sliding down a ramp angled at 47.3 degrees. So here's the ramp, here's the block. The coefficient of kinetic friction between the block and the ramp is 0.210. So I know this angle, I know the mass is going to be 25.0 kg, and I know the angle theta is 47.3 degrees. Right. And we have to draw, oh, and one last thing, the coefficient of kinetic friction is 0.210. We have to draw a free body diagram showing the forces, draw in and calculate the tilted x and y components of weight, find the force of kinetic friction, and find the block's acceleration down the ramp. So the first step is to draw the forces. Now, gravity, or weight, pulls straight down, and that equals mg. The normal force is perpendicular to the surface, so that's going to point up and away like this. And there's going to be one final force, the force of kinetic friction, Fk. Alrighty then, we can get started so that's part A. Here's the free body diagram. We're done. Now let's move on to part B. We have to draw in and calculate the tilted components of weight. So I'm going to draw these in red. Oops. There's one component, there's the other. This one we call the tilted x component, and this is the tilted y component. They also are sometimes called the parallel component. So this is also called the parallel component since it's parallel to the surface, and this is called the perpendicular component because it's perpendicular to the surface. You could also call it the normal component, right? Because it's normal, just like Fn. Okay, now we have to find what those are equal to. We use some equations. You look and you say, okay, this here, Wx, we could slide it down and put it right here. And if we did, we would form a right triangle, and this angle would be equal to 47.3 degrees, the same as this angle. And there's a little geometry proof to prove that that's right. So Wx is a leg of this right triangle, and every leg of a right triangle is either r cosine theta or r sine theta. So this is the opposite leg. Therefore, Wx equals r sine theta, because it is opposite the angle. Right? That means we can find Wx using this equation. And you plug in, for m you plug in 25.0. For g you plug in 9.81. Whoops. I erased. G. M you plug in, G you plug in. For theta you plug in the angle that's given, 47.3. And you calculate the answer, and you get 180 rounding to 3 sig figs. Good. Now we can find Wy. And Wy is the other of these two legs of the right triangle. Right, so here's the right triangle that I'm outlining. And Wy is adjacent, it forms this angle, so it's the adjacent leg of this right triangle. So the adjacent leg is always r cosine theta. So that's how we find Wy. We use r cos theta. And you plug in the same values that we used. Whoops. So this is going to be mg cos theta. For m, you have 25. G is 9.81. Theta is 47.3. And Wy comes to a whopping 166 newtons. So there's parts A and B. I'm going to erase, and solve part C next. So the next thing that I have to find is the force of kinetic friction. And the force of kinetic friction is always mu k. And then you have to multiply by the normal force, right? And the normal force is equal and opposite to Wy. These forces cancel each other out. And the reason they cancel is because the block isn't accelerating off the ramp and it's not sinking into the ramp. So they cancel. And so Fn, therefore, is going to equal Wy, which is mg cos theta. So you plug in your values. Mu, you plug in the value of 0.210, m is 25, right? That's what goes here. G is 9.81, theta, take cosine of 47.3. And what you get there is 34.9 newtons. Okay. So now I'm going to erase again and solve for part D. So in part D, we're asked to find the acceleration. And to do this, we're going to use F net equals ma. Now the net force is simply equal to the net x force. So in place of F net on the left side here, I can plug in F net comma x. And the reason is because the y forces cancel out. They perfectly cancel, this balances out this, and therefore we don't have to consider them at all because they go away. The unbalanced force, the net force, therefore will simply be the unbalanced x force. So in place of F net x, I'm going to plug in Wx minus Fk. And I set that equal to ma. Right? So it's going to be easy to solve for acceleration. You plug in the value that we got for Wx, that was 180, except you use an unrounded number, right? And you plug in the unrounded value of Fk, 34 point blah blah blah, and you take the difference and you divide by m, which we see here is 25, and the acceleration that you receive as the answer is equal to 5.81 meters per second squared. And that's how you solve. So here's another ramp problem with a block sliding down a ramp. And in this one, we are given the angle, theta, is 37.8 degrees. The mass of our block is 46.2 kilograms. Let me draw the block in. And what else do we know? The acceleration is 2.15 meters per second squared. Whoops, that should be a squared. First, we draw the force diagram with the forces. It's not really a free body diagram because we show the ramp. So the fact that we have our ramp here in the picture disqualifies it as a free body diagram. It's actually a force diagram that we're drawing here, just a technicality. So weight, as always, pulls down, W. Normal force pushes up and away so that it's perpendicular to the surface. So that and that make a right angle. And the final force is friction, Fk. And of course we've got equations for finding these things, right? And now we're ready to move on to part B. Calculate the tilted x and y components of weight. Alright, we can do that. Let me draw them into my diagram. Here's the y component. Here's the x component. And of course, the angle, 37.8, is also equal to this angle I just marked. This angle here is 37.8. Okay, Wx is r sine theta, because Wx is opposite. If I bring Wx down here, it's opposite the angle, which makes it r sine theta. And in place of W here, in place of the weight, right here. I'm going to plug in mg. So you insert your values. Mass, you plug in 46.2, 9.81, theta, 37.8. And what do you get for the x component of weight? You get this, 278. Right? Wy, same thing, but instead of sine, it's cosine. Because Wy is the adjacent leg of that right triangle. And then here you do mg cosine theta. So we plug in, m is the same value, g 9.81, theta, you plug in that. And the value you get for Wy is this. The next thing to do is find the kinetic friction on the block. So to find the kinetic friction, we're going to have to use the acceleration we were given. Whoops. Now, F net x equals max, right? And the acceleration down the ramp is 2.15 meters per second squared. So we could really change a here to ax. Right? Okay. In place of F net x, I'm going to plug in the two forces in the x direction. So on this x-axis, there's only two forces, Wx and Fk. So I plug in Wx here. I have to subtract Fk because it's going up the ramp, which I call left. I've taken up the ramp to be the negative direction. And I solve for Fk by plugging in values, right? So Wx is the previous value, 278, minus Fk. Plug in for mass, you get 46.2. And you plug in for acceleration, 2.15 meters per second squared. And although that's messy, you can kind of follow. So you solve, and the value of kinetic friction that you get is 178. Good. So now that we have that value of kinetic friction, it's pretty straightforward to find the coefficient of friction. So I'm going to erase and solve. Okay, the equation with kinetic friction in it and coefficient of friction is this. We know we're going to have to use this equation because it's the only one that has mu, right? So that's naturally the equation we use. To solve for mu, you plug in. You need to know two things to find mu. You have to know this and this. And we know both of those because we've already been asked to find them. Fk is 178. Oh, we actually don't know Fn. We haven't calculated that yet. So Fn is going to be equal to Wx. So we do know it because, Wy, these two forces are equal because they cancel each other out. One points up, one points down. So the magnitudes are equal. And we know then Fn is the value we got for Wy, 358 newtons. So you solve for mu, 178 over 358. And of course you use unrounded values when you plug in here and here. These should both be unrounded. You only round at the very, very end. And what do we get for our answer? 0.498. And of course, this value mu, the coefficient of friction, it happens to have no units at all. It is dimensionless, so it has no units. So you just leave it there like that. Okay, here's the final problem. It was number 13 from our handout. The largest squash ever grown had a mass of 409 kilograms. Alright, write the given down. Suppose you want to push a squash with this mass up a smooth ramp that's 6 meters long and makes a 30-degree angle with horizontal. So the distance of the ramp is 6.00 and the angle is 30. You push the squash the applied force that you give, F applied, is 2080 newtons. That's how much you push with up the incline. The first thing to find is the net force on the squash. Then we find the net acceleration. Then we find the time required for the squash to reach the top of the ramp. Okay, here's my squash. I'm going to draw it over here, being pushed up the ramp. That angle is 30. Here's the squash. And the forces on it include weight, which is mg, and that's acting at the center of the object. Then there's the normal force, and then friction. Oh, there's no friction in this problem. They say nothing about friction, so we assume it's a frictionless surface. So let me see if I can erase my friction here. No friction. The last force then is simply the applied force, which points up the ramp. F applied. Like always, we are going to break the weight into the tilted y component and the tilted x component. I'll call it wy and wx. Right? So to find the net force, we can either take Fa minus Wx, and that will equal the net x force. And of course, the net x force is the exact same as the net force because there's no y net force. These two cancel, so they don't contribute to the net force. So we could do it that way, Fa minus Wx, or we could use F net equals ma. Now clearly we don't have the acceleration from this problem, so we're going to have to use these forces, adding them up to solve. So you take the applied force and you subtract Wx to get the net x force, which equals the net force. Right? It equals F net x, and it equals just plain old F net, because F net y is 0. So to find F net, you plug in 2080 newtons, and then you're going to have to subtract Wx, which of course is the x component of the this right triangle here. It's the x component of that triangle. And the way that we find the x component, well, it's opposite the angle. So it's mg sine theta. Like that. You plug in mass, 9.81, theta is 30. And for F net, you get this value here, 70 newtons. And that's a crudely rounded answer. I don't recall what the real answer is, but I know that that was incorrectly rounded. All of our givens have 3 sig figs, right? This has 3 sig figs, this has 3, this has 3, that has 3 sig figs because the last one doesn't count. So this really should have 3 sig figs when we report our answer. I don't know why it's been rounded incorrectly by our book, right? And any good teacher blames any kind of error like this on the book, on the handout. Okay, that's how we find F net. The next step of finding the acceleration is very, very straightforward because we use the equation F net equals ma, right? So we can find A by taking F net, which is 70, and dividing by the mass, which we were given, 409 kg. 70, and again, this should be the unrounded value, not actually 70 here. It should be whatever you actually got as the answer. And then you keep it unrounded here. So that number over 409 is 0.2 approximately. And again, it looks like the book is rounding to it's rounding to 1 sig fig, which is odd, but that's what it is, you know. And so you actually have probably a better answer in your calculator. Round whatever you get in your calculator to 3 sig figs. And of course, the net force and the net acceleration are both going up the ramp, so they're both directed at 30 degrees above horizontal, here and here. right? So now that we know F net and the acceleration, well, now that we know acceleration, it's easy to find time. This problem is really just a simple problem with our kinematic equations of constant acceleration. We're supposed to assume, now this is unclear, but we're supposed to assume VI is 0, right? We know the acceleration, it's 0.2 dot dot dot, keep all of the decimal places, meters per second squared. We know delta x, the displacement, that's going to be, what was it, 6? Even though I wrote it as delta d here, it really is also the displacement up the ramp. And the last thing that we know, the thing we're looking for is time. That's time, delta t. So the equation we use, the one with these variables, is delta x equals vi delta t. But since vi is 0, the whole vi delta t term is 0. So then we just have 1/2 a delta t squared. So to solve for delta t, right? To solve for delta t, we're going to do 2 delta x over a square rooted. You plug in your values. Delta x is, like we said, 6. Plug in 6 times 2, 12 over 0.2 dot dot dot. Take the square root of that answer. And you get as your final answer something around 8 seconds. And again, round it to 3 sig figs. And that's the solution. That's how you solve these problems.